Hello, Chem 2, and welcome to the next section, section 4.2, about acid-base reactions, a very specialized type of aqueous reaction. So let's talk about what acids are. In Chem 1, you were introduced to the concept of an Arrhenius acid or an Arrhenius base. And an acid is any compound that has hydrogen ions. So it might be HCl, H2, SO4, H3, PO4. They all start with H. And an Arrhenius base was anything that has a hydroxide. So it might be sodium hydroxide, iron hydroxide, aluminum hydroxide, anything that has a hydroxide as its anion. Those are acids and bases. Well, in an acid-base reaction, what's going to happen is acids are going to be their compounds are dissolved in water, and so are bases. Their compounds are dissolved in water. Now, they come in two varieties. They come in the strong variety and the weak variety. And the difference is not whether they're going to burn you, because some of the worst acids in the world are considered to be weak acids. Strong acids are ones that completely ionize when added to water, which means they are 100% soluble. So when writing our net ionic equations, we're going to write them as separate ions. So HCl becomes H plus and Cl minus. HCl is a strong acid. As opposed to weak acids, they're written as molecules. So HNO2 is weak, just written as HNO2. Now, how do you know whether something is strong or weak? Well, unfortunately, one of the things we're going to have to at this point, is without expression of scientific experimentation, is we need to memorize a list. And luckily, there's only a handful of strong acids and a handful of strong bases. So strong acids, they 100% dissociate. We talked about that. Weak acids don't. And here are the strong acids: hydrochloric, hydrobromic, hydroiodic, chloric, perchloric, nitric, and sulfuric. That's it. Now, this is going to be monumental because I'm going to share this story on video. Had a former student of mine, sweet, sweet, sweet girl, kind as can be, but she had a really interesting way to remember her strong acids. She came to me one day and said, "Mr. Farron, I came up with a neat little mnemonic to help me remember this." I says, "Go ahead and tell me what it is. It kind of might be interesting and see if it's one I've never heard." And I hadn't, but I keep sharing it every single year. She said, "Here's what it is. I cleaned the bathroom 3 or 4 times. My mom said, no, 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 it's not clean enough. So I threw acid in her face." Kind of scary a little bit, but it was the way she remembered it. These are the 7. Every other acid that's not on here, every single other acid that's not on here is considered weak. So when you have any of these compounds in your solution, then you split their ions apart. Any other acids, you write them as staying together. Strong bases do the same thing. Strong bases split apart into pieces. Weak bases stay together. So here are the strong bases. You should recognize this list. This is the hydroxide list. Hydroxide solubility rules, where hydroxides are insoluble except group 1, strong, and calcium, strontium, and barium. This is the insoluble list, or the soluble exceptions to hydroxides. These are the ones that are exceptions. Hydroxides are normally not soluble, but these are the ones that are. So since they're soluble, we split them apart as individual parts. Now, there's 2 main types of reactions that take place with acids and bases, and one is neutralization, and one is just gas formation. Neutralization is an acid with a base coming together and then make a salt and water. A salt is any ionic compound. And normally that ionic compound is one that's soluble in water. And then water is a molecule. So water is a molecule. So when we write this in our net ion equations, we're going to leave this together because we leave molecules together. With gas formation, there's two that you're going to have to remember. There's acids when they react with sulfides and acids when they react with carbonates. When they react with sulfides, one of the compounds we're going to make is the gas of hydrogen sulfide, H2S, and a salt, which may or may not be soluble. Carbonate is going to make, let's see, the hydrogen and the carbonate are going to come together to make H2CO3. And then that is going to immediately break down into carbon dioxide and water. So even though this carbonic acid may exist very, very, very small time, it immediately breaks apart into its ions to make carbon dioxide and water. So that's going to be my bubbles, carbon dioxide. So when I take a carbonate and react with acid, I'm going to see bubbles. So for example, if I wanted to write the net ionic equation for a reaction between acetic acid and aqueous potassium hydroxide, acetic acid, potassium hydroxide makes potassium acetate and water. Well, acetic acid is weak. This is strong. This is soluble. And this is a molecule. So only the potassium acetate gets split apart on the product side, and the strong base gets split apart on the reactant side. So only the potassiums are spectators. So we have acetic acid plus hydroxide gives me acetate and water. And that is my net ionic equation. Same thing here. Phosphoric acid or phosphorus acid and lithium sulfide produce lithium phosphate and hydrogen sulfide. This is a weak acid. This is soluble. This is soluble. And this is a gas. Gas stays together. Solubles get split apart into their ions. Weaks stay together. The only thing that is common on both sides are my lithium. So I get to cancel those out. So neutralization reaction, you're going to create the water. The water is molecular, so it stays together. And there's a little bit more about weak, but that's all from your book. So when figuring out how to do with an acid-base reaction, does this formula start with a hydrogen ion? Yes, then it's an acid. No, then it might be a base. Okay, knowing which one's which. Worry about reacting the hydrogen species with the hydroxide species to make them combine. So if it's a weak acid, you just leave it together. If it's a strong acid, you split it apart. So that leads to, one more time, this concept of molarity. So concentration, as we know, molarity is a relationship between the amount of dissolved solvent and the amount of the solution, or molarity. So moles per liter. We're going to use the same exact concept again. Now we're going to deal with aqueous solutions of acids and bases. So we might ask ourselves, what is the molarity of a solution when formed when I take 10 grams of sulfuric acid and dissolve it in enough water to make 100 milligrams of solution. So if I have 10 grams, if I have 10 grams of sulfuric acid, and sulfuric acid's molar mass is like 98 per mole, and I'm going to get a number of moles. Let me use my calculator real fast. 10 divided by 98. And I get 0.102 moles. And then I'm going to divide that by my volume in liters, which is 0.1. So this solution is going to be 1.02 moles per liter. What if I wanted to figure out how many moles are in 5 milliliters of 6 molar? Well, I have, again, I'll put it up here so that I didn't give myself space here. 5 milliliters at 1,000 milliliters per liter times 6 moles per liter. Liters cancel, milliliters cancel, and I'm stuck with 0.030 moles of HCl. So next type of question would be one where we want to know how much reaction, how much components could be produced. This is stoic. I have 6 mils of a 6 molar solution, and I react it with its hydrochloric acid, and I react it with 2.5 grams of sodium carbonate. How much sodium chloride can be produced? So here's my reaction. Hydrochloric acid reacts with sodium carbonate to give me sodium chloride, water, and carbon dioxide. I know information about I know information, my marker, there we go. I know information about the hydrochloric acid. I know that I have 6 mils of 6 molar. And I want to know how much sodium chloride is going to be produced. So first thing I need to do is walk it through stoichiometry. 6 mils at 1,000 mils per liter, mils cancel. 6 moles per liter of hydrochloric acid, liters cancel. I have a 1-to-1 ratio because there's ones here. 1 hydrochloric acid for every 1 sodium chloride, so moles of hydrochloric acid cancel. Know the molar mass of sodium chloride is 58. That gives me that I could produce 2.1 grams of sodium chloride. Now, the question is, it's reacting with 2.5 grams of sodium carbonate. So, what about the sodium carbonate? It's 2.5. Is it going to work? 2.5 grams. So I know something about the other reactant. This is a limiting reactant problem. So I'm going to do the same thing. 2.5 grams divided by the molar mass of sodium carbonate. Grams cancel. Still 1-to-1 ratio. Moles cancel. And 58 grams per mole. Moles cancel. So I could produce 1.74 grams of sodium carbonate, sodium chloride. It's just stoichiometry, just like from the last video. At the end of the last video, I showed you a couple examples of how to do this. This is another example, but now we're talking about acid-base reactions. Still a reaction that exists between two aqueous solutions. Now, there is one very, very specialized type of reaction, and it's called a titration. And we'll put this on to the next video.